First speaker this morning is Joyce from the University of Chicago. He'll tell us about kinematic flow and differential equations for cosmological correlators.
Great, thanks so much. Yeah, it's really nice to be here. This is a little bit different from the usual crowd that I interact with, but I'm trying to learn to talk to mathematicians, so come talk to me and help me out. So I'm going to try to tell you a little bit today about, broadly speaking, cosmological correlators, and in particular, some of the work that we've done in the last couple of years with this cast of characters, including Nima and Hayden, who are here. So if you have any questions, also feel free to ask them. So I think particle scattering amplitudes are somewhat familiar to most of this crowd, but maybe cosmological correlators are not. And one lesson I abstracted from the talks yesterday is that it's useful to start by sort of defining the space of things you care about. And so let me give you sort of a bird's eye view of what cosmological correlators are. And what they are is they're a function of n momentum 3 vectors. So they're a thing, you feed it n momentum 3 vectors, and it outputs a number. And these momentum 3 vectors are required to satisfy momentum conservation. So they form sort of a closed polygon in the plane, if you like. And an important distinction compared to scattering amplitudes is that these momenta are not null. They do not square to 0. And consequently, the length of these momentum vectors is going to be important in the story. And one way of thinking about it is the analog of Mandelstam variables that appear in particle scattering amplitudes are things like the lengths of these vectors and the diagonals of the lengths of the diagonals of this polygon. And just to inject some physics, one way to think about why the energies, if you like, I will call these things the length of the momenta energies, why these things matter, is that in cosmology, like our universe explicitly depends on time. The universe today is not the same as the universe a billion years ago. And so consequently, the cosmological correlators can directly depend on energies. Yes? Here it will just be positive definite, like the R3. You can think of these as living in R3 if you like. Yes. Okay. All right, so let me just, since I think people are familiar with the idea that physicists like to scatter particles and stuff, but you may not be immediately familiar with why we want to study these objects that I introduced on the last slide. So let me just give you some physics motivation for why we care about these things. And it's because fundamentally the things that we measure in cosmology are statistical, right? So my friends go to telescopes, they look out at the sky, and they do things like count galaxies. And no one actually really particularly cares if you look at that direction in the sky, if there's a galaxy precisely there. The thing that we care about is how galaxies are distributed relative to each other, right? So the thing that is meaningful are the correlations between the positions of galaxies on the sky. So very explicitly, if you go out to map some galaxies, what you care about is how likely are there to be galaxies certain separations away from a given galaxy. Okay, and so explicitly, the sort of correlation function its strength depends upon the positions of these objects in the sky. And so here's a totally explicit example. So if you look at, say, the 2-point function of galaxies, which tells you how likely you are to find galaxies at certain separations, it has some sort of non-trivial structure depending upon the distance. And so there's a particular distance where it's more likely to find a galaxy. Okay. Since the universe at large scales has approximate symmetries, it's approximately translation invariant, it is useful to package the information about the position dependence of these correlations in Fourier space by Fourier transforming. And so fundamentally, these correlation functions will be functions of the spatial momenta, right, that comprise the real space function. Okay. And so this is why what we care about is some function of a bunch of momentum vectors. And of course, these are functions that arise from physics, so they're not totally random functions. They have interesting properties. And these interesting properties are a consequence of the physics that generated these correlations. Okay, so because these things were generated by physics that's, say, local, causal, unitary, the functions of these vectors are interesting functions. Okay, and part of what we want to do is to discover what the properties of these functions are and how they encode physics. Okay, why do we want to do this? So precisely because these things are not random functions, but they're functions that contain information about physical evolution, we can learn about the universe by measuring these things. So my friends go out and they count galaxies in the night sky. And then what you do is you trace the correlations between the positions of galaxies back in time to, say, the cosmic microwave background, which is where the universe became hot. And you can relate the correlations and the positions of the galaxies in the late universe to hot and cold spots in the cosmic microwave background. They're really the same correlations. And by understanding how these correlations evolve through time, you learn something about what's in the universe and where it came from. And fundamentally, there's a limit to how far back we can go. So what cosmologists do is we trace correlations through time. And there's a limit. We can go back to sort of this surface where the universe thermalized and became hot and dense, which we call the hot Big Bang. And on this surface, we infer the pattern of correlations. But fundamentally, we can't look past that. And we don't know for sure where these correlations came from. Because of their properties, we infer that they came from an earlier epoch in the universe's evolution that we call cosmic inflation. And so by measuring the pattern of correlations, fundamentally what we're trying to do is to understand the physics of this very early phase of the universe, understand the physics of inflation. And so one way of thinking about it is that studying these correlation functions either tells us about inflation, or if you want to phrase it as some sort of big picture question, studying these correlations tells us about the origins of the universe. That's the thing we want to get access to. Okay, congratulations, you all graduated. You're all now cosmologists. You can pick up your diplomas at the end. This is everything you're going to need to know about cosmology. Okay, so today what we're going to do is we're going to study these cosmological correlation functions in a simplified toy model, right? So the actual theory that corresponds to the real world is a bit more complicated, but it shares many of the features of this simplified toy model. And so we can actually get quite far by studying it, and it has many interesting properties. Okay, so I think actually I might be the first person to write down a Lagrangian. So we're going to actually study this concrete model, and it's really the simplest possible thing. It's just a scalar field theory with a conformal mass in 4 dimensions with a phi cubed interaction. And I'm going to put it in a very particular kind of cosmological background. I'm going to assume that the space-time metric takes this form, where the scale factor is just the power law in time. Okay, and so this parameter epsilon is capturing sort of the non-trivial cosmological dependence. Okay, and so some familiar values of epsilon. If I set epsilon equal to -1, this time factor goes away, and I'm actually just studying a model in flat space. If I set epsilon equal to 0, I'm studying a model in de Sitter space, which is what we think this early universe phase looked like. And then there are other choices of epsilon that correspond to sort of other evolutionary phases in the universe's history. And so by studying this thing sort of as a function of epsilon, we're capturing information about many different types of cosmological epochs kind of in one succinct way. Okay. And so to kind of give away a bit of the punchline, sort of the reason why I'm talking to you all is that eventually what we'll see is that correlations in this toy model can be cast as kind of Euler type integrals, which then is a bit is in the world of kind of combinatorics. Okay, and I should say many of the nice features of this model, most of the things I'm going to tell you, at least in flat space, were understood in this nice paper of Nima, Paulo Benincasa, and Postnikov. Okay. Okay, very good. Okay. So the actual object that we're going to study is a slightly more primitive object than the literal correlation function. And so I told you what we're interested in understanding correlations between things at different points or different momenta in Fourier space. And much like in quantum mechanics, if you want to study correlations, sort of the right thing to do is to think about the wave function. Okay, so in quantum mechanics, if you have the state of a quantum mechanical system, the way that you extract observables from it is you square the wave function and then integrate over all saved positions, right? So if you want to understand the most likely place to find the particle, you convolve the x operator with the square of the wave function. Okay, so similarly here in quantum field theory, there is a wave functional, okay? And so if I want to compute correlation functions of fields at some points in space-time, what I can do is square the sort of wave functional and then do a path integral over all field configurations. So what the wave functional is, if you like, is a probability distribution for field configurations on some spatial surface. And another way of thinking about it is it's just packaging information about the state of the system. It's just a representation of the quantum state of a system. So fundamentally, we think the correlations in cosmology were generated from quantum mechanics. And so what we want to do is to describe the state of the universe at the end of inflation. Okay, and the way that we describe that practically is by writing down the wave functional of that state. Okay, so here's just a picture of how this wave functional can get built from fluctuations of the vacuum. So the wave functional here is just the representation of the vacuum state of this interacting theory in the basis of field eigenstates. Okay. So it is useful, we're going to be computing things in perturbation theory, and so it's useful to parameterize the wave function in a way that's amenable to computing things in perturbation theory. And so we parameterize the wave functional as the exponential of these kind of kernels convolved with field fluctuations and then integrated over all possible momenta. And fundamentally, these kernels, which I will call wave function coefficients, are the objects that have the information about correlations, right? So these are slightly more primitive objects than literal correlation functions, but they have all the same information, and they're capturing information about the state of the universe, or the state of this field theory, if you like. And for our purposes, the reason that this is a nice thing to study is that we can compute this thing using Feynman diagrams. So it's very similar to the world of computing particle scattering amplitudes. We can draw some Feynman diagrammatic expansion that defines these objects. Okay. So it's useful to just give a simple example. So here, as a matter of principle, now everything is known. I handed you a Lagrangian, and I told you what the objects are you want to calculate, and there's like a Feynman diagram way of calculating them. So let me just tell you the rules, and then I'll tell you sort of a simpler way of proceeding. But as a matter of principle, you can go home if you want and try to calculate some of these things. The rules are very simple, at least in this toy model that I wrote down. So we're interested in computing things at some fixed moment in time. So you draw a little line corresponding to that time surface. And now if you want to compute, say, the wave function coefficient for involving 4 momenta, you draw all possible graphs that have 4 lines touching this time surface. So here there's just this graph and other permutations of it. And there are 2 different rules depending upon whether a line touches this late time surface or only connects internal vertices. So if it touches this late time surface, you use this particular plane wave propagator. If it is an internal line, you use this kind of more complicated Green's function for the bulk-to-bulk propagator. It's very similar to the ordinary Feynman Green's function for scattering amplitudes, but it has this additional extra piece that's important because we're computing the wave function. And then for each vertex, you include a factor of t to this epsilon power, where there are different t's for each vertex. And then you integrate over all possible times. And that's integrating over all possible orderings of how interactions can take place in spacetime. So for example, this concrete 4-point diagram corresponds to this integral expression. And so then the challenge is to just sit down and do this integral, if you like. So that's one way of conceptualizing the challenge. But of course, much like in particle scattering, there are typically better ways of doing this than actually explicitly evaluating Feynman diagrams. Okay, but as a matter of principle, you could iterate this to whatever order you want, and there's a concrete integral expression for all possible correlations in this model. Okay. In order to get some kind of handle on what these objects look like and to start to think about better ways of understanding them, it's useful to specialize to a simple case first, which is let's first set epsilon equals -1. And so we're actually just studying correlations in flat space. Okay, so everything on the previous slide gets a bit simpler because these time integrals, these factors of t, all go away. And so now I'm just integrating a bunch of plane waves where the complication comes from the fact that there are certain time orderings, and I have to be careful about the nested time integrals. Nevertheless, you can do this. So the simplest example is if I want to compute the cosmological correlator or the flat space wave function correlator involving 3 external particles. In this case, there's no time ordering to worry about. I'm just doing this integral. I just get a simple rational function. That's nice. At 4 points, I now have to be a bit careful about doing the time integration, but there's no problem. You can do it. And what you get by doing this is this slightly more complicated, but still rational function. So it now involves these kind of 3 factors. And this is kind of nice. There's already a kind of hint of something interesting going on, which is if you actually look at this time integral expression, it has 3 different pieces. And each of them individually are not that beautiful. But then when you add them up, they form something simpler than their individual constituents. And so that's already a hint that there's something nice going on. OK, so as a matter of principle, we could keep doing this. But there's a better, more efficient way of getting the same answers. So this is a conference about combinatorics. So let me try to give you sort of a combinatorial construction / definition of this wave function. And then you can go home and build any endpoint function you like. OK, so just from the examples that I showed you, the flat space wave function is a rational function. And so it suggests that there should be some kind of simple way of building that thing. OK, so it turns out there is. We can kind of build it via a combinatorial procedure directly in the space of kinematic objects. OK, so remember, an endpoint function depends on a closed n-gon of kinematic vectors. And so the first thing, well, at least the first thing I learned to do when someone hands me a polygon is triangulate it. And so in this way of thinking about things, the sort of triangulation of this kinematic object corresponds to a particular way of partitioning the momentum vectors such that particles interact in spacetime. So in particular, this particular triangulation of this pentagon corresponds to assigning the momenta to the external lines of this particular graph. Okay, and so here you see that like momentum 1 and 2 add up to this internal thing, and that corresponds to this little triangle here. Okay, so in flat space, it actually turns out that nothing really depends on the individual momenta or energies flowing out to the boundary. And so it actually ends up being quite useful to kind of consider a truncated object where I just kind of group the energies associated to all lines emanating from a vertex that go out to the boundary together, and think of this object as a function of kind of the sum of energies that flow out to the late time boundary. Okay, so in this particular case, I will kind of group together k1 and k2 and call it just this variable x, which please don't confuse with position. K3, I'll call this variable x2, and then k4 plus k5, I'll call this variable x3. And so the final answer only depends on these kind of sums, k1 plus k2, k4 plus k5, which I've called these x's, and then the internal energies I've called y. Okay, so the final object only depends on this. So now we want to do some operation on this graph that reproduces the wave function. Okay, so let me just tell you what the operation is, then we can try to understand it. So basically, we're just going to circle the graph. Okay, and what we're going to do is we're going to circle the graph, enclosing as many vertices as possible. But the only rule is you're not allowed to draw overlapping circles. Okay. All right, so we go back to this simple 3-point case. So that corresponds to a graph with 1 point. This one is a bit boring. There's one way to circle it. Okay, great. You circle this graph. There are sort of 3 lines that I'm ignoring that pierce the circle, or correspondingly, you can think there's like energy xi flowing through the circle. And so what we do is we take 1 divided by all the energy kind of flowing out of this circle. So in this case, I just get 1 divided by the energy xi enclosed by this circle. Okay, that's cool. Now we can do the same thing for this kind of 2-site single exchange thing, which corresponds to a 4-point function. So here I can draw 3 circles that are all compatible. One is a circle that encloses the entire graph. And then there are 2 circles, one that each enclose an individual vertex. Okay, and then these circles correspond to these factors in this rational function. So for the blue circle, it encloses the entire graph. So the energies x1 and x2 emanating from these vertices out to the boundary pierce this circle, the blue circle. And so I get this factor x1 plus x2. And then the red circle has the energy x1 flowing out of it. And then it also pierces this internal line, which has energy y. And so I get this factor x1 plus y. And then I get the same thing for the right vertex. OK, so these examples are maybe a bit boring because there's kind of a unique thing you can do. And so you just get sort of a single term when you do this. Starting at 3 sites corresponding to correlating 5 points, something kind of interesting happens, which is there are kind of 2 legal ways of circling this graph, right? And they correspond to the choices of where to put this purple circle, right? You can either circle the left 2 vertices or the right 2 vertices, but you cannot encircle both. It's just not allowed by the rules. And so what you're instructed to do in this case, where there are multiple ways compatible with the rules, is you just sum over all possibilities. Okay, so in this case, there are 4 circles shared by the 2 ways of doing this. That's all of these factors out here. And then the two purple circles correspond to these two factors here, and so you add them up together. Okay. And one can check totally explicitly that this reproduces what you get by doing all of these complicated time integrals. If you were to do all the time integrals, you would get some 9-term expression for the same rational function, which you can then check simplifies to this case. Okay, but as a matter of principle, you now know enough to compute any endpoint function in this toy model that you want. And so you can go home and kind of play with it and observe various phenomena. Okay, so yeah, so I encourage you to do this. It's actually quite fun. Okay, yeah, and from this, you can implement recursion relations and things like that. So it's possible to compute very, very high order objects in this theory and observe their properties. Okay, so if you're interested, I should just say, if you're interested in like some more physics background for like what we're doing and why, hopefully at someday we'll finish these lecture notes. But in the meantime, if you scan this QR code, here's a preview of sort of some of the physics motivation and more examples of computing these objects if you're interested. Okay, so let me tell you some of the things if you do. So yeah, if you like the homework exercises to go home and compute some of these things and stare at them. But let me give you sort of the answers to the homework. Let me tell you some of the things you will find if you do this exercise. Okay, so first I should say, you could ask sort of like, why is this working? What is going on? It seems like there should be some interesting underpinning to this whole story. And one way of conceptualizing that is that the flat space wave function is actually the canonical function of some positive geometry. And one way of thinking about it is that this story about summing over circlings is some particular triangulation of this object. It's like a decomposition of the canonical function into simplex forms. And of course, because there's some invariant thing, there are many other possible triangulations. Okay, and these correspond to other representations of the object, like for example, the one you get from explicitly doing time integrals. Okay, I won't say too much more about this, but yeah, there's many nice facts about this object are discussed in this paper. Okay, another thing that is very important in the context of particle scattering is where functions are singular, right? And so we might want to scrutinize where the flat space wave function is singular. Okay, so purely in the space of kinematics, there are kind of two natural kinds of kinematic limits you might envision taking, where you might think that something interesting happens. Okay, so the first one is actually something that can happen for real kinematics, which is you degenerate this kinematic polygon such that some of the momenta become collinear. So here, for example, in the context of this pentagon, you can imagine moving this vertex so that it's collinear with these other vertices. And in the space of kinematics, what that means is that the sum of these side lengths will add up to 0 in that kind of configuration. For obvious reasons, we call this like a folded configuration. It's kind of like you're folding this kinematic object or this polygon to be sort of one vertex less. It turns out that actually, so since this thing can be realized for real kinematics, you actually don't want things to be singular there because we don't measure infinity in the real world. And so it would kind of actually be bad if things were singular there. And it turns out that actually the physical objects of interest are totally regular there. And this is actually an important constraint that we're going to place on the objects, is that they're regular there. If you like, at some point, we're going to have differential equations that these objects satisfy. We're going to need some boundary conditions. And some of the boundary conditions are going to be that the actual physical objects are regular in this kinematic limit. Okay, so that's one thing you could imagine doing, is try to take this kind of folded kinematic limit. Another thing you can imagine doing, so as we learned yesterday, it's often a very, 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 very useful thing to do to complexify stuff. Okay, and so one thing you can do is you can imagine analytically continuing the momenta in order to make the perimeter of one of these polygons vanish. Okay. So for example, you can imagine, of course, you cannot do this for all positive side lengths, but if you imagine going off into the complex plane or allowing some of the energies to be negative, you can make the perimeter of, say, this triangle vanish. And so in the space of kinematics, what that corresponds to is having the side lengths 1 plus 2 and the internal side length add up to 0. Okay. it turns out this is the interesting thing to do. So it turns out that cosmological correlators, or the cosmological wave function, will be singular in this kinematic limit. Okay. Okay, so it turns out this is the good thing to do. And so one way of phrasing that back in the language of the graphs that we were staring at, so you can imagine translating this statement about subpolygons back into a graph statement. And it tells you that the wave function is singular when the energy flowing into some subgraph vanishes. Okay, so roughly speaking, what's going on is that in cosmology, because the time, well, let's say because the universe depends on time, energy does not have to be conserved locally in these processes. And so in particular, the strength of correlations can depend on energies. But if the energy flowing into some space-time interaction happens to add up to 0, something interesting happens, which is you get a singularity. And you can think of this singularity as being kind of an echo of the flat space energy conservation delta function. Okay, and so the actual coefficients of these singularities are going to be related to scattering processes. Okay, so we can see this, excuse me, in action in this very simple example. So remember, I told you this simple example where I have a 4-point function coming from a single exchange is given by this very simple rational function. And just by staring at it, you can see it's singular when the energies flowing either into the whole graph or into parts of the graph add up to 0. Here it's like a simple rational function. You can just read that off by staring at it. Okay, so there's one specific case of this general phenomenon that's extremely important. So the important special case is when the total energy flowing into the graph happens to add up to 0, so that the actual process just conserves energy. Okay, and the reason that this is an important special case is that the coefficient of this singularity is the corresponding scattering amplitude in flat space. Okay. So in a concrete sense, if you take the flat space wave function, you force the energy involved in the entire process to add up to 0. What you will find is that this thing has a pole, and the coefficient of that pole is the corresponding particle scattering amplitude. So in some sense, this talk is like an advertisement for cosmological correlators. And so if you like scattering amplitudes, you should also like cosmological correlators, precisely because cosmological correlators have amplitudes in them. So that's one way of thinking about it. Another way of thinking about it is that cosmological correlators are a deformation of scattering amplitudes away from the locus where energy is conserved. And so all of the interesting structure that exists in scattering amplitudes should have some similar deformation into this larger space. Okay, so that's a nice connection between the study of correlation functions and scattering amplitudes. Okay, so in addition to this, there are these singularities where the energy flowing into some subgraph vanishes. So here's a concrete example. You have some kind of complicated graph. You could imagine the energy corresponding to this subgraph happens to add up to 0. In that case, you will find that the wave function is again singular. And the coefficient is related to the scattering amplitude of the subgraph whose energy is conserved, and then multiplied by a wave function of kind of the leftover graph, or an object that can be built out of the wave function of the leftover graph. It turns out to have some kind of funny energy shift. Okay. And one way to think about this is that in particle scattering, if you go to the point where an internal particle goes on shell, the amplitude factorizes into two kind of distinct space-time processes. And here, this is sort of the analog. So there's an analogous place where you go to some special locus of kinematics where this object splits into lower point objects. It just turns out in this case that the lower point objects, one is an amplitude and one is this kind of related to the wave function. Okay, so it obeys kind of a slightly more interesting splitting property than amplitudes. Okay. So I just want to mention briefly, so everything I've been saying so far is just for the theory of kind of a single scalar. And what I'm doing is I'm fixing the external kinematics so that I only care about a given space-time process or a given graph that contributes to correlations. But there's an interesting thing to do, which is to introduce more scalars and have them interact in a restricted way. Okay, so what we can do is we can give the fields more labels, and we can force them to interact sort of in this trace phi cubed way. And the result of doing that basically just forces us to sum over either all possible triangulations of this polygon, or said another way, it forces us to sum over all the different exchange channels that can contribute to a given process. Okay, so I told you all of these things about kind of a given triangulation, but as you know, it's often much more interesting to sum over all possible triangulations. And so this is a way that kind of forces you to sum over all the possible triangulations of this kinematic object. And so there's, again, sort of a combinatorial way of building the wave function in this trace phi cubed theory in flat space. And the thing you should do instead of summing over sort of circlings of this graph is what you should do is you should take collections of non-overlapping subpolygons of the compatible with the triangulation that you have picked. And then what you do is take one divided by the perimeter of all of the polygons, the product of the perimeters of all of the polygons appearing in the triangulation. And then you sum over all possible collections. So the analog of there being kind of two incompatible ways of circling this graph corresponds to the fact that there are two incompatible collections of subpolygons for this particular triangulation, where the choice I have to make is whether I want to include this purple quadrilateral or this purple quadrilateral. Okay? And then if you want to build the wave function in this trace phi cube theory, you do this exercise for all possible triangulations of, say, this pentagon. And so it suggests, so much in the same way that amplitudes in trace phi cube theory are related to the associahedron, here you're looking for an object that sort of expresses the compatibility between collections of subpolygons rather than between triangulations. Okay, so I think this may be just mostly an advertisement for Nima and Carolina. They have, I think they found this object, so you should ask them about what this object is, but it seems to be an interesting combinatorial object. Okay. All right, so that's all I want to say about flat space. This, in principle, is a talk about cosmology, so let's turn on cosmological evolution. Okay. All right, so it turns out it's a very simple deformation of the discussion that we've already had. So one way of thinking about it is that in this very simple toy theory, going to a cosmological background corresponds to just making this coupling constant that appeared multiplying the interaction in the theory time-dependent, giving it this time dependence that depends on the cosmological background. Okay? And so one way to deal with this, probably the most convenient way to deal with this, is to imagine going to Fourier space. So this is some time-dependent coupling constant. It's useful to treat that thing in Fourier space. So this thing corresponds to this frequency integral. And what we see is that, remember, for every vertex in the Feynman graph, we introduced a factor of this coupling constant. And here what we see is that the effect of this in Fourier space is to shift the energy at that vertex by omega, and then multiply by omega to the epsilon and integrate over epsilon. And so by just following this procedure, what you find is that the FRW wave function, or the wave function in this cosmological background, takes the form of an integral over the flat space wave function. Okay, and so this whole time we've actually been studying properties of the integrand of the cosmological wave function. Okay, so in this way, the cosmological wave function takes the form of sort of a twisted Euler type integral, where the flat space wave function is the integrand. Okay, and so this was not, I wasn't wasting your time or anything. We're actually, we've been studying things about, say, the singularities of the integrand of the cosmological wave function. Okay. So this is just saying sort of the same thing I just said, which is that the flat space wave function, so it's very nice as an integrand. It's a rational function with linear factors, so it depends linearly on the integration variables. So remember what I did was I took the flat space wave function, I take the energy associated to each vertex in this graph, I shift it by its own personal omega a, then I multiply it by omega to the epsilon, and I integrate over all the omegas. And so this thing is going to be linear in these omegas because the original psi flat was linear in the x's. Okay, so that's nice. And so what that means is that the FRW integrand is related to hyperplane arrangements. Okay, so now you all know better than I do that, like, if you have an integral related to a hyperplane arrangement, it's very nice. It's like the Disneyland of integrals. And so in principle, you can proceed algorithmically, right? So there's some hyperplane arrangement. The hyperplane arrangement cut out some number of bounded regions. And so you know that in principle, there will be at most that many master integrals. So you just enumerate a basis of master integrals, take derivatives of the thing that you want to integrate by parts to rewrite it back in the basis, and you're guaranteed to get some differential equation at the end of the day. Okay, so there's no in principle obstruction to doing this. Okay, so let me show you how this works for the only example I can actually draw. So for the 4-point function, so this is the cosmological 4-point function coming from an exchange. So remember, this is the same integrand I was drawing before, which has 3 linear factors. It's just the flat space cosmological wave function shifted appropriately. So this thing corresponds to this hyperplane arrangement. Okay. Sorry, this is a typo. This should be in the omega-1, omega-2 plane. Okay. So this thing, it has 3 hyperplanes associated to the linear factors of the integrand, and then it has 2 hyperplanes associated to these twist factors. And in this space, the actual FRW integrand corresponds to the canonical form of this triangle, which is bounded by these hyperplanes. Okay. And so just by staring at this picture, you know that psi has to be part of a 4-dimensional family of integrals, and so it's totally possible to just enumerate a family. It turns out to be useful to choose the canonical forms associated to the various bounded regions. Okay, and so for us, very concretely, it was useful to choose the canonical forms of these 3 smaller triangles and this big triangle. And one nice optimization, which at least was new to us, is that by choosing as your basis the canonical forms of these bounded regions, it's automatic that the differential equation is an epsilon form. You don't have to do any manipulations to realize this. And one way of thinking about that is it turns out that the derivatives of canonical forms with respect to sort of their kinematic variables and their integration variables satisfy nice relations, which kind of guarantees that this will be true. So this is sort of a nice way of organizing the basis. Okay, so in this particular case, you just get some differential equation. The details here are not super important at this point. So I've just grouped all of the master integrals into some vector, and then you can write this matrix differential equation in this form if you want. One point I want to make at this point is that notice that there are new possible singularities that appear in the differential equation that were not there in the integrand. So these singularities are the same singularities that appeared in the integrand. When you start taking derivatives, you see that these new possible singularities appear. And so as I said before, one of the boundary conditions that we place on the actual solutions to these equations is that these singularities cancel out. Okay? And notice that these singularities are kind of the friends of singularities that were already there. So there was this singularity which corresponds to where the energy in, say, the left vertex adds up to 0. And this is kind of the friend of that singularity, but with this minus sign for the internal energy. And so this thing would be singular in this folded configuration. And so we want to forbid those singularities from being. Okay. All right, so at this level, this just kind of is what it is. So you see this differential equation, you can imagine solving it. It's not that big a deal. And there's no in principle obstruction to going to higher points and considering more complicated graphs, including things with loops and so on. Okay. And in fact, we did this. So we followed this algorithmic approach up to like 7 site graphs or something like that. The integral basis gets very big. You start staring at these very complicated matrices, trying to understand what's going on. But as you go to very large numbers of points, what you find is that both the final answers and all of the intermediate steps seem a bit complicated. And so it kind of feels like you're not doing the right thing, right? So you start to ask yourself, like, is there a better way of organizing our information? Because at the end, you always find that there are kind of these big matrices, but they have like very sparse entries. And so you're kind of like, okay, what is going on? There must be some better way of thinking about like where there are 1s and 0s and stuff like that. Okay. So we spent quite a long time just kind of staring at this stuff. And one thing we realized is that it's like useful to draw pictures. Okay, so I think probably it's not very difficult to convince a bunch of combinatorialists that drawing pictures is useful, but you know, it was new to me. Okay, so it turns out to find just some graphical representation of the equations that we were writing down. Okay, so first it's useful to relate the kind of letters that were appearing in the differential equation to the tubings of some marked graph. Okay. And roughly speaking, you can think of this as being just sort of the underlying graph that was computing the wave function from the time integral, but now with some additional dressing that allows us to discriminate between whether the internal energies are positive or negative. Okay. So here is just a dictionary to translate these sort of d-log forms that were appearing in the differential equation to tubings of this graph with a little x. And so the rule is just that if you encircle a vertex, you get d-log of the energy flowing into that vertex. Or if you encircle the whole graph, you get d-log of the energy of the whole graph. But if you circle a vertex plus its kind of neighboring cross, you assign a minus sign to the internal energy that the circle pierces. Okay, and this way you can enumerate all the possible singularities that appeared in that differential equation. Okay. It turns out that you can also assign some sort of graphical representation to all of the functions that appeared in this integral basis. And here the rules are very similar. There's again an underlying marked graph. But here the rule instead is you want to completely circle every vertex, right? And now you have to decide when you circle a vertex whether you also include the cross or not. And there are sort of 4 different ways of doing this, right? So you can either just circle the 2 vertices separately. You can encircle this vertex, including the cross, and this guy separately. You can do kind of the opposite of that, or you can encircle the entire graph. And it turns out that the number of ways of doing this exactly matches the number of functions that appear in the differential system. And so it's very easy to relate these sort of graphical pictures to the functions that appear. Okay, so now we've kind of encoded both the information about the letters appearing in the differential equation and the function in some tubings of a marked graph or circlings of a marked graph. And so now we can rewrite the matrix equation that I showed you a few slides ago in this kind of pictorial form. Okay, and at this point, it may still not be totally obvious what's going on, but you do start to notice some patterns, right? So you start to see the same objects kind of appear. So this guy appears here, and then also this guy appears here and also has a friend here. This guy appears here and then also has a friend here, for example. This guy just appears by himself. And so you start to see that there's sort of some structure to what letters multiply what functions. Yes? Sorry, say it one more time. Yes. Yeah. So if you, so it's the same. If you wanted to count the middle vertex of the 3-side chain as just flipping the sign of the corresponding energy. Yeah, that's right. Yeah, there's no, the crucial distinction is you're not allowed to circle this cross by itself. Okay. Okay. So it turns out, one can kind of see just from these pictures that roughly speaking, the differential equations that we're writing down correspond to some kind of like growth in the space of tubings. Okay, so as an example, the differential equation, so this was the original differential equation for this 2-site wave function. So it corresponds to this combination of functions and letters. And it turns out it can be read off from this kind of like flow graph family tree kind of thing, where there's some set of rules for how the tubings can kind of grow as you move along the branches of this tree. Okay. And the important thing is that there's just kind of a set of rules that tell you how to construct something like this, and then how to read off the differential from it. So let me just tell you, sort of declare what the rules are, and then we can try to understand them a bit. Okay, so the procedure is the following. So I want to compute the differential equation satisfied by the cosmological wave function associated to some graph. And so I, start with the graph of interest, and I mark all of its internal lines. Okay. If I wanted to, I could imagine I never have to say anything about space-time. I could just say I start with some kinematic object, I triangulate it, I write the dual graph to that triangulation, and then I mark it. And now what I do is I associate the letters that will appear in the differential equation to sort of one tubings of this marked graph. So I think about all possible ways that I can write a single tube enclosing vertices. Okay. And depending upon whether I choose to enclose a cross or not, it tells me whether I flip the sign of the internal energy that the tube pierces, or that pierces the tube. Okay. So in this case, for the 3-site chain, I have to draw these 2 markings, and then there are 13 ways of doing this, writing a sort of a single circling of various adjacent vertices and crosses, and they correspond to these letters that appear in the differential equation. And if you're curious, this procedure grows polynomially in the number of vertices. Okay, so this specifies the letters that will appear in the differential equation, sort of the possible locations of singularities of the functions that appear in the system. Okay, but then we also need to know what the functions are that will appear in the differential system. And these things correspond to, so I'm going to avoid saying tubing. So for us, there's an interesting thing that would be nice to discuss, which is that there are various notions of circlings of graphs that appear in this story. And they're not quite literally the sort of mathematical definition of tubing. But in some cases, they seem very natural. And so it would be interesting to understand whether this is a useful thing to do more generally. So here I will avoid saying the word tubing, although in the paper we say tubing. So here we sort of write down these so-called complete circlings of the marked graph, meaning that we circle all the vertices involved in this marked graph. And here you can kind of grade them by how many vertices you enclose in circles that also enclose a cross. And so here, this thing where I just circle the 3 vertices and no crosses corresponds to the original function that is the wave function. And then 1 level down, there are circles that enclose 1 cross. Here, there are circles that enclose 2 vertices and crosses. And these are circles that enclose 3 vertices and crosses. There's an interesting thing, at this moment is a curiosity, but I'd be very interested to know if there's a more principled explanation, which is that the alternating sum of these things vanishes. Okay, and this seems to always be true. Okay, and in general, this procedure actually grows exponentially. So this thing goes 4 to the number of edges appearing in the original graph. Okay, so for the 3-site chain or the double exchange, there are 16 ways of doing this, which correspond to the 16 functions that appear in the integral basis. Okay, so that is sort of the arena in which we are living. We have a set of letters that will appear in the equation. We have a set of functions that will appear in the equation. But now we need kind of the interesting thing, which is the differential of a function. That's sort of what it means to get a differential equation. And so we need a rule in order to read off the differential of a function. Okay, and so here it's a little bit more obscure, but I'll just tell you what happens, and then we can talk about it. But the point is you start with the graph that's associated to the function whose differential you're interested in computing. Okay, and now we draw kind of a flow chart of all possible ways that this circling can grow, or this tubing can grow. And what you do is first you march through the graph and you activate each of the circles. So you imagine lighting up this circle and then asking what it can do, lighting up this circle, asking what it can do, lighting up this circle. Okay, so that's this first level. You just march through and activate each circle. Then it turns out that if you activate one of these gray circles that doesn't already enclose a cross, it is allowed to kind of grow by absorbing the cross next to it, or engulfing the cross next to it. And if it happens to overlap with another tube, you just kind of merge the 2 tubes by taking their union. So in this particular case, you kind of light up this gray circle. And so here I've drawn it gray because the gray ones can kind of eat the cross next to them. And so you light up this gray circle, and then it can grow to the right, eat the cross next to it, and kind of merge with this guy. Okay, so that's what this step is. There's another example down here where this gray cross can kind of grow to the left, eat its neighbor, and kind of grow into this larger tube. But if you light up a tube or a circle that already has a cross, it can't do anything. It just sits there. Okay. That all kind of makes sense. It's not very obscure. There's one slightly obscure thing, which is that if you happen to have an activated tube or an activated circle that has a cross, and that cross is pointing to another circle, this thing can eat the circle next to it. Okay, so in this particular case, you kind of light up this circle. It grows to enclose the cross. It's now sitting next to another circle, but since its cross is pointing at that other circle, it can eat it. Okay, and so this is some slightly additional rule that you have to account for, but it's actually very important. So you get the wrong answer if you don't include this. So it's like it's super super important, but also kind of the most obscure feature. Okay, so roughly speaking, this is the whole thing. You activate these tubes, they grow to enclose crosses near them, and then they can kind of also merge in the direction of their cross. Okay. All right, so that's good. So this is a procedure to generate this tree-like object corresponding to these like colored-in circles. And then once you have this object, so getting this thing is sort of the thing that's slightly obscure, but once you have this object, reading off the differential of this function is super easy. So if you want the right-hand side of the differential of this function, the sort of activated tubes, you just march through this graph, and for each thing that appears in this tree, you write down the letter corresponding to the activated tube. And then the functions that multiply that activated tube is the function corresponding to this same picture, kind of ignoring the fact that this is colored in, minus the function associated to its immediate descendant. So you just kind of march down the tree. So for example, the differential of this function would involve this letter multiplied by the function corresponding to this graph minus the function corresponding to this graph. And then you just do the same thing for all the letters that appear here. Okay. Okay, so this is nice. Let me just give you an example. Let's go back to this two-scythe wave function. So its differential can be read off from this picture. And so if you just translate what I just said into equations, you find that the differential of this function corresponds to this equation. And then you can check that indeed that is the right answer. This is what you get by doing things in this sort of integration by parts way. Okay. Okay, so this is basically the story for this type of integral. That you find that for each function appearing in this basis here, you just do the same thing. For each function, there's a corresponding kind of tree-like structure. From that tree-like structure, you can read off the differential. And then putting them all together, you get the differential system obeyed by all of the functions that appear. Okay. And this structure persists for kind of arbitrary graphs. We did many different examples with different topologies. It also works for the loop integrals and things like this. Yeah, for loops, I want to distinguish. So it works for the time integral part of loops. There's still a challenge to do kind of the loop momentum integrals. Okay. One thing I want to emphasize is that I basically just gave you a definition for a differential. But in order for that definition to be consistent, it better be that it squares to 0. And from this point of view, it's like super not obvious that that should be the case. Okay. And you can kind of, if you really get into the details of what's going on, you can see that the fact that the differential is nilpotent sort of depends on two kind of interesting features of the whole system. One is that the sort of kinematic letters, the letters appearing in the differential equation, obey these kind of interesting three-term identities, which, for example, for the two-scythe graph, correspond to identities like this, that the total energy is equal to sort of the energy flowing into this left vertex plus the energy flowing into this right vertex with a minus sign. So it's kind of a trivial identity. And it has this kind of graphical picture that this thing can be thought of as like kind of the union of these two pictures. And there are many such three-term identities. And you find that d squared is kind of always proportional to these three-term identities. So there's something like a bit special. And you can ask, like, why are these things true? These things are true because this integral came from a local space-time process where you know, the energy flowing across this vertex is related to the energies coming out of the graph. Okay, and so there's some kind of interesting imprint of locality in the fact that this differential is actually a true differential. And then the other thing is that you can try to like mess with the assignments of signs, factors, minus signs, like factors of 2, whatever. And you find that you really need everything to be precisely what it is in order for the differential to be nilpotent. So there's some very rigid structure here that, to be honest, we don't totally understand. Okay. One piece of physics I want to input quickly is that as you go to higher and higher points, the size of the family of functions appearing, or the size of the integral basis, gets rather large. We already saw some like small example of this in the context of this single exchange or this two-site graph, where it was part of a four-dimensional system. And just on general grounds, that guarantees that this thing will satisfy some sort of fourth order differential equation, or as you go to very high points, these things will satisfy very high order ODEs. But there's another kind of thing that's special about these objects that come from local space-time physics, which is that they accidentally satisfy much, much lower order differential equations than they had to. So there's already a baby version of this for this single exchange or this two-site graph, which is that you would expect this thing has to satisfy a fourth order homogeneous equation. It actually accidentally satisfies a third order homogeneous equation, or said another way, this kind of second order inhomogeneous equation. And in this case, it's very easy to see why that had to be the case, because this thing came from a local space-time process with a propagator that satisfies a wave equation. And so you can imagine acting with that wave operator on the exchanged particle, and it will kind of collapse the propagator and give you kind of a local contact-like interaction, right? And so translating this space-time equation into equations in the space of kinematics leads to this second-order differential equation, okay? And there are many more, even more dramatic versions of this that happen at higher points, which is that the actual true physical objects satisfy much nicer and much lower order differential equations than they necessarily had to. And this is obviously related to the fact that this came from some local space-time process, right? And so it would be nice to kind of reverse engineer and understand, what I should expect to happen at the level of this first order differential equation in order to guarantee that the objects of interest satisfy these kind of lower order differential equations. Okay. One other thing I want to say is that, so here I gave you a very like space-time motivated introduction to these objects. We literally started with a Lagrangian, drew Feynman diagrams, transformed those into interesting integrals, and then tried to do the integrals. If I was like a little bit more adventurous, I would never have said anything about space-time. I would have like started with a polygon. I would have said, we're interested in functions of the shape of this polygon. Let's think about what we can do to it. And you would think that, okay, one thing you can do is triangulate it, associate a graph, maybe mark the graph 2-bit, things like that. So there's sort of a very adventurous way of giving this talk, where I just start in the world of combinatorics, which maybe for this audience would have been the right way to go. And then the output of this whole story would be some object that has a space-time interpretation. And if I told the story that way, it would seem a bit bizarre. You would say, okay, why are the set of rules or the things you're telling me, why does this have anything to do with space-time? And I mean, that's of course very intriguing, because we would like for there to be a description of cosmology where space-time is not a central player, where it has some emergent ontology. And in order to make this sort of the reason I didn't quite tell the story this way is it would have seemed slightly arbitrary, in the sense I could have given you a prescription for doing these things, but it wouldn't have necessarily seemed inevitable, right? And so, a challenge maybe that we can discuss is there some way of starting directly in the space of kinematics that makes this whole story like totally inevitable? There's like a rigid mathematical structure defined in terms of these objects. And if you're interested, so we did tell some version of this story in this paper. So if you're interested in sort of how it would work, you can look there. Okay, but yeah, it was, alas, not quite adventurous enough today. Okay, so let me just conclude with sort of some interesting questions, right? Or questions for you all, or things that we can discuss. Yeah, there's this sort of interesting fact that the alternating sum of the number of functions graded by this particular grading happens to vanish. It suggests there's some interesting organization of them. Yeah, to be honest, I gave you some prescription for how to read off the differential of the functions. I don't, at a really deeply principled level, know where this comes from. I mostly just showed you differential equations, right? But in cosmology, we actually care about solving these differential equations. We know how to do this in many cases, but it would be nice to have a sort of more systematic study of the types of functions that arise from doing these types of integrals. There's a whole interesting story about adding additional labels to this particle so that you're forced to sum over all possible triangulations. And there's an interesting generalization / deformation of this story to study other models. So here I focused on a particular model of a conformally coupled scalar in a power law over W space. But it turns out that the correlation functions of massive particles in de Sitter have a very similar structure that's deformed in a kind of interesting way that I can tell you about. And then there's an interesting challenge in cosmology, which is to actually do loop momentum integrals, which are kind of more complicated versions of these types of integrals, which often involve more non-trivial curves, and so need some new ideas. Okay, I'll stop there. I'm happy to take questions.
Okay, questions? Yes, Julio.
You quickly mentioned it at the end of your talk, but do you have a feeling for what type of functions show up in the result? Like more than polylog?
Yeah. So so in the cases that we have done, I can tell you what happens. Yeah, so in this case, if you actually integrate this equation, this is actually just a hypergeometric equation, so you just get a hypergeometric function. At 3 sites, what you get is some Comte de Fourier function when you have 2 exchanges. When you have 3 exchanges, my expectation is you'll get some 3-variable generalized hypergeometric function. So these are all kind of in the world of generalized hypergeometric functions. When you take the limit epsilon goes to 0, they reduce to polylogs. And so the sort of de Sitter conformally coupled scalar is in the world of polylogs.
Okay.
You showed for the n equal 2, so the 2-side chain, every function you chose was corresponding to a simplex?
Yes.
Better?
No. So they can be, so what we do when we do things systematically is you can always write the basis functions as a sum of simplex forms. So they'll triangulate something. But it's not true that all of the bounded regions can be just taken to be simplices in general. Yeah.
Any others? Yes.
So in the case where you have the massive scalars, as you said, do you expect any of these differential equations to still, I know the propagators change, right? But the position of the singularities, does it change?
Yeah, so the trick basically is you can write, so in the case where you have massive scalars, as you know, the mode functions become kind of general Hankel functions. But there's an integral representation of the Hankel function as an integral of a rational function times an exponential. And so you can cast the wave function involving massive particles, again, as kind of a generalized Euler type integral. But now there's a difference, which is that one way to think about it is that there's now an additional structure to the graph. So there's like now an honest marking in the middle where the internal energies on the right and left don't have to agree. And you kind of integrate over all possible partitions of energy. And so they're at the level of the integrand are new singularities that are not there for just the FRW wave function. But as a matter of principle, like the integrand is still realizable as like the canonical form of some hyperplane arrangement and stuff like that. So the integrand still is related to sort of like linear factors. And so formally the brute force approach still totally works. This sort of more elegant approach, I don't quite know what the deformation of the rules are yet.
So on the screen it says Nima raises hand. I don't know if it works. Can we unmute Nima?
Do I have to do something or?
Hey, guys, sorry,
Okay, anybody else other than Nima?
I'm now unmuted.
I
Can you hear me?
turn on my sound, I guess, but that might be a problem.
Tried this before.
Sorry?
We should have tried before, I don't know.
All right.
Maybe Dima can type the question.
Can you hear me okay?
And you should be talking on the phone.
I could unmute my computer, but I'm worried it will.
Someone can guess what Nima's gonna ask.
Okay, Carolina, why don't you ask Nima's question?
Sorry.
Can you guys hear me okay? No?
You can now.
All right.
Since we're now, okay, since we're currently 6 minutes behind, how about Carolina, your best guess what the question could be?
Time.
I think he's probably gonna clarify something. I don't think he
Okay.
can. That's my guess.
All right.
Okay, I'm sorry, we can't quite hear you.
Okay,
That's fine. That's fine.
Wait, sorry.
okay. Well, how about we,
There's a way to go from the differential equation to the time integral.
Ah. Very good, very good. We talked about this at some point. I think so. I'm not entirely sure. It's kind of related to this thing we talked about, related to like the Schrödinger equation, right? There's sort of a different way of twisting the integrand that gives the Schrödinger equation. How to translate that into the, yeah, starting from the differential equation. Yeah, I don't quite know how to reverse engineer it, but it sounds like it should be possible.
yes,
The question is about this epsilon. So like you're interested in the limit, then epsilon goes to 0, right? That's like the physical.
That would be the physical case, is kind of the small.
Does epsilon has by itself, and then it's not 0, has some physical meaning?
When it's not 0.
So if epsilon is not 0, can it have some physical?
Yeah. So it actually, in the context of like inflationary cosmology, epsilon is the time derivative of the expansion rate of the universe, right? So it's telling you kind of how quickly it's like the acceleration of the universe, broadly speaking. And it turns out that that might sound kind of obscure, but actually this parameter is like literally something we measure by measuring the spectrum of temperature fluctuations in the CMB. So this parameter actually tells you how the power in temperature kind of changes as a function of scale. Because this parameter changes a little bit during inflation, and inflation actually encodes time into scale in cosmological correlation functions. So by measuring the power in cosmological correlators as a function of scale, you're actually measuring this parameter at different epochs during inflation. So yeah, it totally is a physical
Is it the
thing.
same epsilon as in Feynman integrals?
I'm sorry?
Is it the same epsilon as in Feynman?
No, it's a different epsilon. It's not like a dim reg parameter. Here it's a kind of, it's kind of a different regulator, if you like. It's like instead of considering exact de Sitter space, you're kind of deforming the geometry a little bit. And it turns out that that geometry is actually physically what happens in inflation, because inflation ends.
so we thank Austin again.